it will just kind of build up. So we can start the introduction. I see Bhavna's recorded. Thank you, Bhavna. So welcome everyone to today's TNZ seminar. So we're going to have a presentation here from Jeffrey Felix, who's the director and also the lead of this BASE GGR competition on the DAC demonstrator. So he's going to present his insights on sort of the DAC demonstration work that he's involved with, and particularly with his company that's doing this demonstrator is CO2, is it Circular Air? Is that right?
Circular Air.
Yeah, Circular. So he'll be providing an overview of the work that they're doing, and then we'll have some time for Q&A afterwards. So if you could kindly just keep yourself muted until the very end, and then we can do questions at the end. And then if you have your camera off, that will help hopefully with the bandwidth, just to make sure that the video is nice and good quality. So thanks, Jeffrey. I'll let you take it away. Thanks.
Okay, thank you very much. Now I need to be careful to switch. Okay, hello everybody. Good afternoon. I'm calling in from the Netherlands. I hope you can hear me, because I have no idea. Yes?
We can hear you very well. Thank you, Jeffrey. Yeah.
Okay. So this session I'm going to introduce you to Smart DAC. Smart DAC, as I just mentioned, stands for Sustainable Membrane Absorption and Regeneration Technology for Direct Air Capture. And yeah, that's what we're going to do. Let's see. My slide doesn't want to. Okay. So this is probably a picture familiar for everybody, because this is what we do. This is what we do as humanity. We use our gas, oil, coal for our human activities, and we generate CO2. Yes. What we would like to focus on is to stop using fossil sources and to use CO2, the C from CO2, as a carbon source for the future, so that we do two things at the same time. We reduce the CO2 in the atmosphere, and at the same time we use the CO2 instead of using fossil fuels. So why this new short cycle? Because we as CO2 Circular strongly believe that in the future we will still need a carbon source for production of our materials, production of our chemicals, production of our fuels. Yes. Having a short cycle, this will accelerate the reduction of the fossil fuel consumption. And by using green CO2 from air, we will not add extra CO2 to the atmosphere. So how do we intend to do this? So our technology has two steps. Yes. First of all, we use membrane gas absorption, which is a membrane technology that uses a membrane as not as a filter, not as a separator, but what's the right word in English? Okay, we'll get to me in a minute. It's to keep gas and liquid separated. Yes, and we use a liquid absorbent. Yes, to on the inside of the membrane. As soon as air touches the membrane is porous, so air will simply go through the pores, and as soon as air touches the absorbent, only the CO2 will be absorbed, because the absorbent has a strong affinity to CO2 and it doesn't like the rest. Yeah. And by doing that, you slowly concentrate your CO2, creating a carbonate or a bicarbonate. And at the moment that you are, let's say, not saturated, but at the required concentration, you switch to a second process tank with your alkaline solution. And at that moment, you start concentrating the CO2 and separating the CO2 from your absorbent in a way that your absorbent is totally recycled, and you get to a very pure 99+% pure CO2. And the impurities are they depend on the humidity. The impurity is water. Yes. Here again, now I know the name. So the membrane is not used as a filter; it's used as a contactor. You see here a porous membrane, a liquid adsorbent on the right side. Yes. The CO2, the absorbent has a very high affinity to the CO2 and reacts to a carbonate and later on a bicarbonate. The function of the membrane is keeping the gas and liquid separated. It's for creating a very a maximum amount of transfer surface area, and is of course meant to allow CO2 to pass. Yes, it's the first step. The second step, the concentration of the CO2, is done electrochemically with membrane electrolysis or electrodialysis, where we, depending on how we use the process, we could even also produce oxygen and hydrogen. But at the present, in the project what we're working on, we suppress the production of O2 and H2. And starting from the potassium carbonate and potassium bicarbonate, we produce a clean CO2 and a clean potassium hydroxide that's totally recycled. So the functionality of this membrane electrolysis step is the concentration of the CO2 and the recovery of the absorbent, and potentially we could also produce oxygen and hydrogen. And in the project we're doing up now, we have suppressed this and used the energy that's in the hydrogen to reduce the energy, the electricity consumption. So why direct air capture? So direct air capture tackles all CO2 emissions. Yes. In general, people tend to focus on industry, but industry produces only about 30% of the total CO2 emissions. And if you take CO2 from air, you do not only focus on the industry, but you also look at the aviation and everything that we as humans produce of CO2 as well. So another thing is direct air capture doesn't influence the industrial process. So compared to point source capture, yes, you do not need to adapt your process to make point source capture possible. And at the same time, every point source is different. So if you take, although the concentration of CO2 is much higher, so it's simpler to absorb CO2, it's also simpler to absorb impurities, and each plant, each capture plant should be designed from scratch, as the composition of the feed in this source is different for each plant. Yes. So furthermore, the DAC is very clean. The air is relatively clean, and therefore it produces a very pure CO2. And what's very important regarding costs, that DAC can be built with a very low number of simple low number of simple and key equipment, simple key equipment. Yes. And last but not least, yeah, we generate a renewable source of carbon. Now, this picture is probably known by many of you. This was part of the webinar of April 1st, I think, 2020. And there, these four removal approach, CO2 removal approaches were presented and compared with each other. Afforestation, DACs, enhanced weathering and direct air capture, and just look for removing 8 gigaton of CO2 per year. You need 400 times less surface area than when you compare afforestation, so planting trees, with direct air capture, meaning that just compare 1 square kilometer or 1 square mile with 400 square kilometers or 400 square miles. And for BACs, it's a factor 2.6, for enhanced weathering, a factor 30, and for direct air capture, a factor 400 compared to planting trees. So what does our CO2 circulares technology, DAC technology, make unique? So we use natural wind instead of fans for the absorption side. So we do not need to put the fans into capex, and we do not have any electricity to use to drive the fans, so zero energy costs. We have a little energy because we need to circulate the absorbent, but the absorbent is circulated with centimeters a second, so that doesn't really cost energy, not comparing to creating wind with fans. So our technology absorbs 24/7. As I presented in the beginning, the absorption is a sort of batch process, because we concentrate from a clean potassium hydroxide for alkaline solution to a solution with carbonates and bicarbonates, and at a certain moment we stop and we switch over. But this means that by switching over directly, during regeneration, we can simply continue absorbing. So we have no alternating absorption and desorption steps. So we can use low-cost electricity for the regeneration. Yes, we use a safe, non-toxic, chemically stable and fully recyclable, regenerable absorbent. As mentioned before, it's a simple unit concept with a small amount of key equipment items. And for sizing up, scaling up, it's scaling up by the numbers, not by the size. Yes. We believe this is an innovative DAC technology with the lowest cost potential. So the commercial side of things. So what's the market? At this moment, to be honest, I don't believe the market is there yet, because nobody is paying for it yet. But as soon as that is going to happen, and then the market will be huge. And although we're not we ourselves are not really focusing on that market yet, but we are focusing on the applications. Of course, we can take the CO2, capture it and put it in the ground. Yes, but we really believe that it's better to find methods to use the CO2. So even use it directly in greenhouses, horticulture, or for fizzy beverages, for other direct use, for packaging, using green instead of gray CO2, producing syngas, producing methanol as an energy carrier, even producing ethylene with as a target producing recyclable polymers, because also then the CO2 is captured and stays captured. From the syngas, it's possible to produce an aviation fuel and also shipping fuels. Aviation is the most complex fuel, I would say, but also as calcium carbonate in the cement industry is a possibility. And we are very interested in everybody who is looking into developing products from captured CO2. So now it gets tricky because I'm going to share a video which more or less summarizes what I just said, and this what I just presented. And this is the video where we got into the finals during the COP26. What I heard, it doesn't really matter, but we got into the finals. What I heard was that over 2,000 companies participated, and we didn't win, but we got to the top 5, and we were the most watched video. So with this video, I will just test if this works.
If we tell you there is $100 billion gold mine right above us for everyone, and no one has ever laid hands on it yet, you might ask why.
I'll just hold it. Did you hear the sound?
Yes, the sound's working. Great. Thanks,
okay.
Jeffrey.
No, I'll do it again. Thank you.
If we tell you there is $100 billion gold mine right above us for everyone, and no one has ever laid hands on it yet, you might ask why. So allow me to explain. Human activities will emit CO2 and continue to do so, together with the 8 billion humans who've created a colossal amount of emission points. But here's the fun fact. Industrial CO2 accounts for only 30% of the total global emissions. So to achieve a zero-net society in 30 years without direct air capture is really erosion. Is it only a problem, or is also an opportunity? IPCC stated the following: all pathways that limit global warming to 1.5 C project the need of direct CO2 removal in the order of 100 to 1,000 gigaton of CO2 over the 21st century. Guess what? $100 billion can be generated out of thin air if only 1% of this 100 gigaton that to be captured is utilized at the targeted price of $100 per ton. And that's the gold mine in the sky. The CO2 captured can be converted to chemicals, fuels, or even directly used in fizzy beverages and greenhouses. So let's vacuum clean the atmosphere by a smart DAC. Think of a pine tree for a second. Do you know that 1 kilometer square of pine trees can absorb up to 1,250 tons of CO2 per year? But here's the deal breaker. At the same space, the smart DAC can absorb up to, drumroll please, more than 500,000 tons CO2 per year. To put things in perspective, the smart DAC is 400 times more efficient than pine trees. Smart DAC is a simple two-step process. In the first step, the wind naturally passes through a permeable membrane gas absorption unit where the CO2 partially permeated through the membrane pores and react with the solvent. The reaction products are regenerated via electrochemical conversion in the membrane electrolysis unit, thereby releasing carbon dioxide, oxygen, hydrogen, and the fresh solvent is recycled back to the first step. A smart buffering strategy was adopted to synchronize the absorption step and the batch type regeneration step to ensure the overall continuous process. Our technology is unique. We've eliminated the need of fans by using natural wind to lower the costs and energy consumption, and we've ensured continuous absorption process of CO2 in a safe and low-cost solvent, using timber as material of construction, and powered the regeneration step by wind or solar, Our technology can also generate hydrogen and oxygen to be used for various purposes. Probably the most efficient and longest DAC technology at below $100 a ton. We're currently designing and optimizing this promising technology together with the team of partners who are striving to build a pilot plant at the capacity of 100 tons of CO2 per year in England, Northern Ireland, or Scotland. Our next stage is to connect with partners and end users to scale the technology to full commercial scale. We're interested to join you for projects to further develop the Smart DAC technology. So let's build the Smart DAC's wooden Roman watchtowers as a hidden wall against climate change. If we tell you there is 100 billion...
Okay. Thank you. Switch back.
Great. Thank you, Jeffrey.
So that's, I think, yeah, I have one more slide, and that's just, yeah, question, cooperate. We are interested if you are. We are looking in all sorts of areas for partners, and that it could be R&D and innovation work focused on direct air capture, but also CFD, tunnel testing. You know, we capture CO2 from wind. So with Harriet-Watt University, we worked on a model to define for what is wind at what location, you know, and therefore CFD could be of relevance for optimizing module designs. But also the direct green use, conversion to chemicals, to fuels, or any other suggestions. So thank you for your attention. Any questions, info co2xair.nl, or look at our website, co2circulaire.com. The final, this is the slide that was presented when I met Pera in London 2 weeks ago, that summarizes our technology. And yeah, I thank you for listening.
Thank you, Jeffrey. So I'll open the floor to questions from the audience. If you do have a question, do feel free to raise your hand, and then you can unmute and ask the question, or you can type the questions into the chat. But I guess I can kick things off, because I think, yeah, it's really interesting to see, because I don't think that I've seen anyone develop this type of technology for DAC yet. So you've seen a lot of the people doing sort of adsorption technology, or the ones with the calciner type of approach that, you know, for instance, carbon engineering have worked on. So this is the first one where I've seen sort of a membrane contactor being used. Yes. And I guess in terms of like coming up with that design, was this something that you just thought, because I guess they use this in also the natural gas for purification processes there already, did you kind of get that inspiration from looking at industry and then tried it out? I'm assuming you did sort of lab-based experiments to kind of test and do proof of concept. Is that right?
No, yeah, that's okay. I can answer that. This no, it was not something we bumped in by accident. It is this technology has been many research time, and much of research has been done in the 90s on this at TNO. And that's the Dutch Technology Institute in the Netherlands, of course. And two of the members of the partners in Co2 Circulaire worked on this in the 90s. And one of them is the head, was the head of the department at that moment, as in process technology. And in the meantime, he is retired, and he stopped many years ago, but by the way, end of the 90s, the top management of TNO said, yeah, but why are we doing this? Why are we looking into capturing CO2 and capturing CO2 from air? Why would you do that? There's no customer. Nobody is interested in CO2. Who is going to pay for this? So they stopped the research. End of the 90s, they stopped the research. And so the individual members continued a little bit. And the Berend Termeulen, who was our CTO, he said, "Oh, we must." And now the times has changed. So he started 5, 6, 7 years ago to look into this deeply again. And then everybody was interested, but nobody was really interested in putting effort, budget, or time in this. So yeah, I met Berend and we talked into this deeply, and then this is everybody focuses on industry, and I said, look, CO2 is not a problem for the industry. It only gets to be a problem maybe now, but if you compare it to 5 years ago, maybe now because governments are forcing industry to do something. But it's not a specific industry issue. And therefore they are interested, but they're not investing money to do something about it. Yes. So, and then we formed a team of scientists. Together, we have over 150 years of experience in membrane technology, and I have specialists really in the electrochemical side and specialists in the membrane gas absorption side, and together, only together, we were able to do this. So we repeated tests on small scale. Of course, materials, membranes have been developed further since the 90s. So what we also do, we use membranes that are available. We could research our own membranes, but let's take it from materials that are available on the market. And that's how we started working on this, and that's how we got invited by the Net Zero Technology Center to work on a project in the UK. Yes.
Thanks, Jeffrey. I see Martin Tressler, you've got your hand up. Would you like to unmute and ask your question, please? Thanks.
Yes, of course. Thank you, Jeffrey. Thanks for the very interesting presentation. Great to see your project progressing.
Thank you.
I might have missed a detail, apologies if I did, but I was wondering if you used the membrane also in the regeneration step or only in the capture step.
Yes, no, the membrane gas absorption is used only in the capture step.
So is the regeneration like a conventional stripping process?
No, that's also membrane-based, so it's membrane electrolysis.
Okay.
Depending on how you apply it, electrodialysis is more known. Yes, and where we also use membranes, and there in fact, we create the split to a concentrated CO2 and a pure absorbent. And this absorbent is fully recycled and reused in the absorption step again.
So is there any scope for going directly, taking the CO2 directly from the solvent into the electroreduction medium, so that you don't have first produce CO2 gas and then go to some other solution phase process to reduce it?
Let's see if I understand that well. So from there are different ways. So if you would, let's say our project, our technology as Smart DAC is now, is focused on taking CO2 from the atmosphere and in fact on taking it from the atmosphere definitively. And what we are focusing on and to use it smartly. So if the approach would be different, or if the objective is different, you could consider a direct use of the carbonates into a next step, into a reaction step, and then later in the process you should at the end, we need the absorbent back. And what you're saying not is that you the electrochemistry step without having it as a gas directly towards a converted product. Is that how I should understand this?
Yes, that's what I had in mind, because if you're going to reduce the CO2, presumably you're going to do that in some kind of electrochemical cell.
Yeah.
So why not keep the CO2 in solution right from the get-go?
Yeah. Okay. I think the answer is yes. It's there are possibilities there. It's not as straightforward, it's not a simple thing. So these are typically research projects that could be done in a country or even Europe-wide to develop, to develop a product. But we need to sort of define which product you would like to develop. But I'm sure it's possible to do that. Yes. And
Thank you.
Thanks, Martin. Yeah, I think there's a good question, Martin, because I think I have seen sort of variations that use sort of electrolysis and they make sort of a solid material, for instance, like a solid carbonate, mineral carbonate material with the electrolysis process because of just the way the reaction works. So I guess it depends what your end use goal is. If you want gas, CO2 or liquid aqueous, the CO2 to remain in the aqueous form, or like a solid material. So there's kind of ways that you kind of
You want gas if you're going to sequestrate it, but probably if you're going to do chemistry with it, there's not particularly advantageous to make it as gas.
Yeah,
one of the projects because that's one of the long-term goals that we have is to we are generating CO2 from wind. So what's more elegant if we would take hydrogen, green hydrogen, also generated from wind, and have those two convert, two products.
So this is a co-generation process, is what you're suggesting,
Yes.
Felix, as it's making hydrogen as well. Yeah, so we've got a question in the chat here from Riley. You mentioned a number of green products that could be generated from the CO2 from direct air capture, and it could be converted to products like methanol. And Riley was wondering if you could comment on the potential scale of each of those different options and how suitable you feel the products are for direct air capture, like your process that you've developed. Do you think there's any issues around suitability of certain pathways?
No, not really. This is all a matter of size. To do this in small scale is relatively expensive. But our next scale, we're now into going to demonstrate it. That's the plant is now we're starting with the detailed engineering now. So in a year from now, it should be more than finished. It should be already tested. And then we're producing 100 tons a year of CO2. The next stage would be 30 to 50 times bigger, which could already be combined with a 5,000 megawatt hydrogen cell. Yes. And then it's already big enough to convert this to, for example, methanol. But it's a matter of size. The size bigger will then, I think after that will be at the scale of 50 kilotons a year. And then you have the lowest costs per ton produced. So the bigger the plant, the lower the costs are to be. And we have to take in mind that a very important part, we have no absorption costs, nearly no absorption costs. We only have the energy if we are producing CO2 in a gaseous phase, yes. for the regeneration. And then it gets to be important how we design our unit, that we have the lowest energy consumption, and that we generate this energy, this electricity, also by wind or solar.
That's really interesting.
It's a matter of size and a matter of, yeah, it states also, yeah, a market sense, a market, you know, if for example we would say aviation fuel, yes, and if governments at this moment, the aviation industry has no other means for their heavy airplanes to be, they need fossil fuel. There's no, you cannot, maybe a small plane you could run with electricity, but a big plane, there's no, that at this moment it's not seen as a possibility. So the aviation industry said, no, we need fossil fuels. And it's at this moment it's still said, all the governments, yes, we understand, there's no limit. But if governments would say, okay, of course you may use fossil fuel because you have no alternative. However, by 2026 or 2027, make sure that 20% of your fuel is sustainable. And then you get a market pull, because then they need a green CO2. If we then would take a green CO2 and a green hydrogen to make synthetic gas, and from that in a two-step process which already exists, that is no abracadabra, it exists. You could make a sustainable fuel, and that will be more expensive, but then 20% is sustainable. But then there's a market pull, then you get action. But for my understanding, that has not happened yet. So I'm not, so that's on aviation. For methanol, it's the same. That's also, methanol would be, you know, electricity. We have in this North Sea, we have sometimes electricity left that we don't know what to do with it. Now, if we would use this energy to produce methanol, then you have a building block that you could store, energy you could store. And that also is a matter of size. So you need a certain size to make that happen. I don't know, does that answer the question a little bit?
Yeah, I think so. So it comes down to scale. You mentioned the need for certain policy measures, for instance, that, you know, mandating, for instance, requirements for more sustainable fuels, and that would then create the market pool that would then hopefully progress and encourage deployment of these types of technology options. So I think this is quite, you know, interesting to hear, and I you know, we'll kind of have to keep an eye and see what the governments are kind of doing and developing. And, you know, in Europe, they're developing these things called like the green taxonomy, which could potentially help create the environment required to kind of reduce carbon intensity of fuels, which then may, you know, displace the fossil fuel and then create a market for sustainable fuel. So I think this potentially is things that are under development and in the process. So at least in certain countries like Europe, that's already happening. The UK, that's happening, and then hopefully, you know, other bigger countries like the US will follow suit. So yeah, we'll be interested to see in that space. And Riley says thank you for your answer. I guess in terms of the sort of question on my notes, because you had a really nice diagram which showed the process, different components, and you mentioned that it was kind of using the natural airflow in terms of, and then that would eliminate the need for instance, blower energy or electricity. In terms of the contribution of that energy in traditional DAC processes, other DAC processes, what is that proportion usually? So air blowing, is that a big proportion of energy, which is why you tried to focus on eliminating that?
Yes, it's a good question, and I know the answer, but I haven't got it by heart. So because I know at the dissemination meeting in November last year, the same question was asked and I couldn't answer it then. I looked it up. I need to look it up again, but it has, I think there's a publication by Cesaro, Australia, that Paul Ferran published a I think in his publication he segments the energy and the capital equipment, the capital cost that is needed to generate the absorption flow, the wind flow. And I have to be a bit careful now because I really don't remember it. I think it would be maybe about 30%.
I was thinking that number too, that for some reason that number's in my mind, yeah.
But I need to look it up again. And I can look it up and maybe send to you and you can share that. But it's the, you know, we think it's possible with wind. And I know it's more tricky, but there are many locations where we have wind. And therefore we focus on England, Scotland, Ireland, Northern Ireland, of course, but also the Netherlands, Germany. There are places in France where there's always wind, yes? And we don't need, also when there's no wind, the absorption will work, only it will be at a little lower capacity. But if together with Heriot-Watt University, we looked into a model to develop, okay, let's say, now London is wrong, but let's say Dover, for example. Yes? We pin Dover and we can define from this model how much wind there is during the year, where the wind comes from which direction, what's the flexibility. So is it mostly northwest or totally different? And what's the wind velocity? So I still think in Beaufort, but you could say in meters per second. It doesn't matter. Yes. How often does it storm? What's the rain, the snow, and other weather like? And we put that in that model, and then we find out that we have average. We have 90% of the time. We have good wind. Okay, then we accept the 10% with too much or not enough wind, and that easily covers for the extra investment that you need to make to put in fans. And if you have a location where you do not have wind, yeah, then we're also sure that there will be no windmills there. And we are forced to move to solar and use that energy. But there are so many locations still where wind is okay when it is available. So let's first use this in a way that it's also elegant, that it's nice to see, that the people that live there don't see that as an issue, because those are other things. The social impact, if you build we calculated, by the way, we also did it for the UK, but I know it by heart from for the Netherlands. To reach the climate goals 2030, we only need, I think, 20 square kilometers of surface, this ground area, land, to put on our absorption units to make that happen. So it's
so
not
that 20 square kilometers. How much capacity would that be capturing in terms of CO2?
That will be 14 million tons per annum.
Okay, that's interesting. Yeah, so I guess that means that for the process flow sheet, that eliminates the need for the blowers would require a location that has very strong or wind availability in order to kind of have that enough flow of air across the membrane.
Let's say focus on 2, 3, 4 Beaufort. So it's not stormy weather. It's just with 2 Beaufort, it's already very nice. 3, 4 is nice. We don't need 8, 9, or 10 because then we need to protect the membranes.
I see. Yeah. So it's kind of somewhere in between. Yeah.
Yeah.
Is it comparable to where, let's say, have you looked in terms of wind turbines, and they've also got a window of operation for wind velocity? Is it comparable to that, so that, you know, you could co-locate your DAC unit, which has, you know, the optimal wind velocities that would also be what the wind turbine also requires? Have you kind of looked into that as well?
To be honest, I did not, but I'm sure that one of the team members did. But I think we can already start at lower, because you know, at zero wind we still have absorption. So, but
really?
as soon as because there's air, the membrane sees air, so the CO2 will be absorbed. But as soon as you start with some movement of air, yeah, then you get an increase of absorption.
That's very interesting. No, I guess be very, when the results come out, because you did mention that BEIS will be publishing the results from the different direct air capture and GGR demonstrations. Is it this year that you mentioned? So I guess would that include a report from your demonstration project as well?
Yes, we have there's a public report that's I think shared per today. It's really hot from the press. I got it from BEIS this morning, the email. I didn't even look what's all reported, but I know we submitted a report which includes quite of the things more in detail that I just presented. Yes.
Okay, great. I guess to the audience, if you're interested in reading more details about the results, that report will be that's available today, that BEIS has published. So yeah, no, it's quite interesting to see. And I guess you know, we're really looking forward to kind of seeing this progress. In terms of the actual plant itself, you mentioned it's kind of still in the FEED design stage, is that right? And then the construction will start next year.
Exactly. So we have defined the location. So our plant is going to be built and operated, or to be operated in Northern Ireland, yes, in Belfast. And so we are now looking for partners up there to help us support. Those are just the companies that are supporting with local construction materials, because that's also our plant will be from plastic, so we try to use the lowest costs material that are able to use to do the job. Yes. And so no stainless steel piping if you can do this with polypropylene, preferably green polypropylene, but that doesn't exist yet. So
so within the actual column, does it require packing material, or is it purely just the membrane and then the liquid and the gas being separated? So you don't need sort of like metal packing. Oh, that's quite. No, it's quite an innovative thinking, because I know, you know, Carbon Engineering also use plastic to reduce the costs, but their technology needs packing material inside the column. And then the problem is using plastic packing is that the contacting absorption performance is reduced by using plastic, because the film that's produced by using plastic packing is not as good as using stainless steel. So they kind of lose a bit on performance when you use plastic components. So it's quite interesting to hear that this technology won't lose that performance, but you're still using plastic to reduce the capital costs.
It's more out of a temperature issue, because there's no heat.
Okay.
In our system, there's no heat, and but you're right regarding the on the absorption side. I think there's a lot of potential research to do to improve absorption capacity, and that will lead. I can tell you, last week one of my lead scientists in membrane gas absorption found a solution to increase his result with absorption capacity of factors of a factor 2 to 3. So that means that in the future the plant could be 2 to 3 times smaller, and this we're still in that range. There is really a lot to be improved, and improvement potential there. Yes, yes.
Yeah. Actually, I have lots of questions really, but I think we might have to wrap up because we are coming to the end of the hour. And then I'd like to give Bhavna some time, I guess, to introduce next week's session. I'm guessing there's no session next week, Bhavna, is that right?
Yeah, sorry, no session next week.
Yeah, because it's a bank holiday for us in the UK,
Okay.
so we don't have a session. But I'd just like to thank you so much, Jeffrey, for your insights and providing answers to the questions that we've had today. I might have gone a bit on the technical route just because I'm just really interested to kind of learn more about this. But, you know, thank you so much for providing your time today. Did you want to say any last words before we wrap up?
Now, the thing is, when I was in London meeting Pira, and the 2 days before I was in Glasgow, I think it's very important for the younger generation, so all the people in this teenage 20s, even 30s, that they see what it's about, because this is a real potential. If we use the C from CO2 as a future non-fossil carbon source, then we have solved part of the climate issue, because then there's no need to burn fossil fuels. And if you see that, yeah, then it's full speed ahead. So thank you for giving me the opportunity, giving us the opportunity to present this. And if there are any questions, please, contact us. Thank you.
Thank you so much, Jeffrey, and thank you everyone for attending today. And if you do have follow-up questions, as Jeffrey said, the invitation is open for you to email him directly. So I'd like to say goodbye and hope everyone has a great weekend. So thank you all for joining.
Thank you.
Thanks everyone. Bye.
Bye-bye.